Introduction to Water-Soluble Polymers. Section 2. Polymer Size and Shape. Probably the most important piece of information about a polymer sample is the size of the molecules. We will discuss how the mass of a polymer molecule is reported and what that means. Also, I will be going over the shape the polymer molecule takes on in solution. Thus, we will be discussing the conformation of the polymer, as briefly discussed in the previous lecture. In order to discuss the mass of a polymer molecule, or a real polymer sample for that matter, we need to first revisit a very introductory topic from general chemistry, molecular weight. You've probably already noticed that I use a script M for molar mass. Just like in your general chemistry class, the molar mass is defined as the mass of 1 mole of molecules, and it has the typical units of grams per mole. In contrast to this, we also have molecular weight. By convention, MW is used to abbreviate molecular weight. It is defined as the mass of just a single molecule, and it has units of either atomic mass units, U, or Daltons, dA. Now, I have a bachelor's degree in chemistry, and I've done more than my fair share of calculations which required the use of molar masses. But I was never aware of the distinction shown here because I knew nothing about polymers. Well, that certainly changed during my graduate studies. Anyway, to me, as a non-polymer chemist, these two definitions were interchangeable. The only difference is the units, right? What's the molar mass of ethanol? Okay, I add up the molar masses of the atoms and I calculate it to be 46 grams per mole. Okay, great. What's the molecular weight of ethanol? Oh, well, I just did the math, and guess what? It's still 46. But now the units give 46 Daltons. What's the difference? Why even bother with having two different definitions? That was my thought. Well, as I will show you, this is not the case when it comes to polymers. There is a very important difference, and these two concepts should not be used interchangeably, although you will find that they still are sometimes. Let's start with a typical polymer sample. I have drawn out just the backbones here, and you can see that each individual polymer molecule has a different length. This is typical. I've even lined them up by increasing lengths for you to see. Now, here comes the dilemma. If I were to ask you for the molar mass of this polymer sample, you would need to figure out how much a mole of these polymer chains would weigh, right? Okay, you could do that, but does that molar mass actually describe every polymer molecule in the sample? No, it wouldn't. It would actually be some sort of average. The problem is that we have a distribution of chain lengths here. Thus, we have a distribution of molecular weights, which leads me to that definition. What is the molecular weight of this polymer sample? You could calculate the MW for each individual polymer molecule, but how do you give me just one value for the entire sample? Again, you could only give me some sort of average, and that's it. So as you can imagine, when discussing actual polymer samples, molecular weight averages are used, and molar masses are not used. Molar masses are still used when describing the monomers, or even the monomer residuals, but not the polymers themselves. Returning to our sample of polymers, let's look at this molecular weight distribution. Since the molecules are already nicely arranged via increasing molecular weight, it is easy to see how they might be placed in bins according to their size. Each bin would represent a particular molecular weight, denoted here as M1 through M5. This setup is referred to as a histogram, once we count up the number of molecules in each bin. For universality purposes, we can generalize the variables by using a subscript I. Thus we can refer to a generic bin I as the ith bin, with n sub I number of molecules in it, which all have a molecular weight of m sub I. This gives us the freedom to split our sample into a few bins, like the 5 I have shown here, or even hundreds or thousands of bins, depending on our analysis technique. Plotting the values from the histogram then yields a plot similar to this, where you can see that the distribution of molecular weights resembles a Gaussian distribution, slightly. The more samples you analyze, the more types of distributions you will see. Personally, this molecular weight distribution plot is the easiest and clearest way to communicate what the sample looks like. However, it is also convenient to summarize these results with a single number. The three most common averages used for reporting molecular weight information are M sub n, which is the number average molecular weight, M sub w, the weight average molecular weight, and M sub v, the viscosity average molecular weight. We will go over some of the details regarding these different averages and something called the polydispersity index in the next few slides. The polydispersity index, or PDI for short, is a measure of how wide this molecular weight distribution is. This can be almost as important as the average in many cases. I remember as a student, the different molecular weight averages never made sense to me. I could use the formulas and calculate the correct averages, but I didn't really understand what they meant. Actually, I saw the same formulas, which we will get into in a few slides, in 3 different courses. It wasn't until the 3rd course before I finally got it. That 3rd course was actually a lab, and the instructor just mentioned M sub n and M sub w in passing, but he explained the difference in a way that finally made sense. He used an analogy to city populations, of which maybe I'll repeat here in a bit. Conceptualizing the difference between M sub n and M sub w is probably the easiest with an example polymer sample. Let's use the 3 polymer molecules shown at the bottom with degrees of polymerization of 10, 20, and 30 for simplicity. The visual representation is accurate and to scale. There are 10 repeat units in the first polymer molecule, 20 in the next, and 30 in the bottom molecule. If we take the molar mass of the monomer residual to be 100 grams per mole, we can start calculating some molecular weights. Whoa, wait! I thought we weren't supposed to use molar masses. Yeah, not for the polymer itself. We can use molar masses for the monomers used to produce the polymers, and we can even use molar mass values for the monomer residuals, the mers, within the polymer. You can easily switch grams per mole to Daltons to get values into molecular weight units. Personally, I use molar mass whenever the size of the item never changes. Here, the size of the polymer molecule changes, but the size of the repeat unit never varies. Anyway, let's compare the procedure for finding the M sub n versus the M sub w for this 3-molecule polymer sample. Because the number average molecular weight is typically how students would go about averaging a value, let's start there. We start by taking each molecule into consideration. We figure out what the molecular weight is for each molecule in the sample. Here, we come up with 1,000, 2,000, and 3,000. How? We simply took the number of mers, the degree of polymerization, and multiplied by the mass of the mer, which is 100 grams per mole, or 100 Daltons, whichever way you want to report it. Now, we simply find the average of these values. This is no different than every other average calculation you've done throughout your life. We add all the answers up, which comes out at 6,000. Then we divide by the number of answers we just summed up. In this case, it was 3. Thus, we end up with an answer of 2,000. So the M sub n of 2,000 Daltons here represents the average size of the molecules in the sample. In contrast to this, the weight average molecular weight begins by considering each mer in the sample. If we are to ask each mer, what is the size of the polymer you are in, we get 10 mers, which all answer 1,000 Daltons. These are all of the mers from the top molecule, in case you were wondering. Moving on to the second molecule, each of its 20 repeat units all respond with 2,000 Daltons. Following suit, the 30 mers in the bottom molecule all give 3,000 Daltons as an answer. Now, averaging all of these values is a little more work than last time, but that's what calculators are for. Summing up all the answers, we get 140,000. Dividing by the number of answers, which is 60 this time, we end up with a final average of 2,333 Daltons. Notice that this value is slightly higher than the 2,000 M sub n we calculated for this sample. This is typical. Actually, if your M sub w is less than your M sub n, you did something wrong in your calculations. But in contrast, I hope you can see how the weight average molecular weight represents the average size of the molecule which each mer resides in. And clearly there is a difference. If you still don't understand how we can get 2 different values, take the example of city populations. Since we're in Minnesota, we'll use the 5.5 million people living here, in about 1,000 cities, depending on how you define a city. Now, what is the average population of a city in Minnesota? Well, It depends on how you get your average. You could go to the city hall of each city and get each city's population and then average those values. You'd get under 5,500 per city on average. Or you could ask each person in Minnesota, what is the size of the city you live in? See the difference? Now the Twin Cities are going to overwhelm your averaging. There are about 400,000 people in Minneapolis and 300,000 in St. Paul. That means a lot of people will all give you really large populations as their answer to your question. Actually, the largest 5 cities compose of almost 1 million people total. That means that 1/5 of the people you ask will give an answer above 75,000. After you get all through 5.5 million people in Minnesota, your average response will be much higher than the 5,500 people you calculated from asking the city halls. The average value you calculate depends on who you are asking, the cities or the people. Similarly, the average molecular weight of a polymer sample differs depending on if you are asking each polymer or asking each mer in the sample. For the actual molecular weight average calculations, we return to our histogram type of setup. Each polymer sample is separated into I bins, each with n sub I number of molecules in the bin, and all of which weigh around m sub I molar mass, or molecular weight. Now, the mole fraction of the ith type of polymers in the ith bin is denoted x sub I, and defined as the number of molecules in the ith bin, n sub I, divided by the total number of molecules in the entire sample, which is the sum of all n sub i's. This leads us to the number average molecular weight, denoted as m sub n, and defined as the sum of all the I mole fractions times their representative molecular weights. Similarly, the mass fraction of the ith type of polymers in the ith bin is denoted y sub I and defined as the mass of the ith bin divided by the total mass of the entire sample. Note that the mass of each bin is defined in terms of the number of molecules times the molecular weight of those molecules. As you probably imagined, this leads to the weight average molecular weight formula in much the same way as the mole fraction led to the number average molecular weight formula. Explicit and longer formulas are also shown here for completeness sake. Depending on your data, sometimes the longer version is more useful. Lastly, the viscosity average molecular weight equation is given here. Notice how the format stays in line with the previous 2 equations, except for now the exponents use a new variable, a, to generalize the formula. This variable a is always between half and 1, and it depends on both the polymer in question and the solvent being used to dilute it. We will discuss this in more detail in the upcoming lectures. One thing I do want to point out though, m sub n is always less than m sub v, which is always less than m sub w. This is a helpful piece of knowledge to keep in mind when working homework and exam problems. Be careful to check your final answers to make sure that they fall in the correct order, and therefore make sense. If you calculate your m sub n larger than your m sub w, you mess up somewhere in your calculations. For additional explanations, see the supplemental molecular weight information on the course site. Beyond the molecular weight averages, the other main descriptor of the entire molecular weight distribution is the polydispersity, or PDI for short. Compared to the molecular weight average equations from the last slide, the PDI has a pretty nice and easy formula. It's simply the ratio of MW to MN. Since the MW is always larger than or equal to the MN, this ratio will be 1 or greater. If the PDI is 1, then the MW and MN are exactly equal, and the sample is said to be monodisperse, since every molecule is exactly the same size. As the PDI increases, the MW becomes relatively more and more larger than the MN. Of course, this means that the molecular weight distribution broadens out more and more. It is not uncommon to see polymer samples up around 5 or even 20 if samples have been mixed. To help you understand how the molecular weight distribution is reported, let's take a look at a polyethylene oxide sample. Polyethylene oxide is oftentimes abbreviated as PEO. Here we have a 40-gram sample. We separate the sample out according to the molecular masses of the individual polymers. This is referred to as fractioning out the sample. We notice that even here we have a distribution curve as we follow the sample levels in the beakers. But even as we look at the numbers, we see that there are more grams of the middle fractions. This is common. So what can we do to begin calculating the molecular weight averages and the PDI? Again, reference the supplemental MW information on the course site for help. I realize the toughest part of these calculations is getting started. For that reason, I'm going to go over how I organize the data when I'm analyzing it. I suggest you start with a good spreadsheet. Since we are given the mass of the polymers in each bin, the mass fractions are the easiest to calculate. We start by summing up the given masses, which should add back up to the original sample size. Here we have all of the samples adding up to 40 grams. Now we divide the mass of each bin by the total mass, giving us Y sub I values. Adding up the Y sub I values better give us 1, otherwise we made a mistake in our spreadsheet calculations. Next, we calculate the amount, in millimoles, of each fraction. To do this, we divide the mass of the fraction by its characteristic molecular weight. For example, the first fraction had 0.5 grams of sample. I divided this 0.5 grams by 5,000 grams per mole to get 0.0001 moles, which is 0.1 millimole. Getting the spreadsheet to do this for each fraction, or row on the table, is a simple task. After this, we can calculate our mole fractions as the millimoles of each fraction divided by the total, 0.515 millimoles in this case. Similar to the Y sub I column, the X sub I column here better add up to 1. Now, calculating X sub I, M sub I values is fairly straightforward. Just make the spreadsheet do the math for you and fill it down through all of the rows. Adding up all of the X sub I, M sub I values, I calculated about 77,500 grams per mole for M sub N, the number average molecular weight. Similarly, calculating Y sub I, M sub I, and summing up, I calculated about 760,000 grams per mole for the MW, the weight average molecular weight. Before moving on, I always like to see if my answers make sense. MW is bigger than MN, so no obvious mistakes. Now, the PDI calculation is easy. Just divide the MW, 760,000, by the MN, 77,500, to get 9.8. This is fairly disperse. The nice part about using a spreadsheet is that you can easily plot the data to show the entire molecular weight distribution. Here, I have the mass plotted on the y-axis. And here, I have the millimoles on the y-axis. Both plots are using a logarithmic scale for the x-axis of molecular weights. This is common, since the range of molecular weights is often pretty high. Also, notice that the same data shows slightly different looking molecular weight distributions depending on what is plotted, mass or moles. Oftentimes, the mass fraction, or mole fraction, is plotted instead. So where do these molecular weight distributions come from in a laboratory? Since the molecular weight of a polymer is one of its most important characteristics, quite a few ways have been devised over the years to measure it. Here I have a table, which is included on the course site, outlining some of the more common methods. I will be going over a few of these methods in greater detail in subsequent lectures, but for now let's just get an overview. NMR is the standard chemical analytical technique for looking at the unique environments of each atom of a molecule. Thus, it can be used to compare how many chain ends there are in comparison to MERS. As you can probably imagine, once a polymer gets too large, the signal peaks from the end units are too small to compare against the overwhelming signals from the MERS. So NMR-based measurements are limited to relatively small polymers, less than 20,000 daltons. However, it is an absolute measurement type, which means it does not require known standards. Because the method analyzes each molecule, it yields an MN value only. Essentially, the NMR is asking each molecule what its molecular weight is, and then averaging those responses. Osmometric methods are similar to NMR methods in that they also give a number average molecular weight, don't require standards, and only work for low molecular weight polymers. In addition, osmometry requires a selective membrane, which makes it a useful technique only for certain polymer types. Viscosity measurements are used quite extensively for industrial cases because it is so cost effective. Yes, it is a relative method, meaning that the system must be calibrated using standards. But this is not a huge setback since most polymer solvent combinations have been cataloged already. It yields the viscosity average molecular weight, M sub V, which we will discuss in more detail when we go over the viscosity measurement technique later. Size exclusion chromatography, known as SEC or GPC even, is the other most commonly used technique. Actually, it has become so common that most instruments are bundled with trays and software that allows for easy automation of sample analysis. This is the easiest method for getting a full molecular weight distribution. I used it in a lot of my own research, and the only drawback is that only linear, or mostly linear, polymers can be analyzed this way. But since most polymers are linear, this isn't much of a drawback. You just need some known standards to compare your polymer to, and you're ready for SEC. We'll cover this method more in depth also. The light scattering method for determining molecular weight is an entire textbook on its own. We won't be going over this technique any further because it is a relatively costly method which requires a lot of time and really dust-free environment. However, as long as you know the relationship between the concentration of mirrors and the refractive index, light scattering can be used as an effective method for measuring not just the weight average molecular weight, but also the radius of gyration, which we will cover in upcoming slides, and other parameters such as A sub 2 and chi. These are definitely beyond the scope of this course, so we'll just stick with M sub W and R sub G for now. Lastly, MWD is a pretty cool technique for natural polymers. It's like the NMR method on steroids, since it is an absolute method, but it doesn't do any averaging. It actually measures each individual molecule. That's how sensitive the sensors are. As a result, the entire molecular weight distribution can be reported. After all that hype, I should point out that it's not a great option for every polymer. In fact, it's a really poor option for most synthetic polymers. I mention it here because it is such a great method for natural polymers, such as proteins. Don't worry, I'll give you a quick overview of the method in upcoming lectures. All in all, there are many options to choose from when looking for a method to characterize the molecular weight of a polymer sample. Knowing which types of values you'll need helps narrow down the options. To help you understand all of these techniques, and polymer behavior in general, let's take a look at how polymer molecules behave in the bulk and in solution. Polymer characterization oftentimes relies on the shape of the polymer molecule. In general, polymers tend to have a high degree of flexibility. Unlike small molecules, which have only a few carbon-to-carbon bonds, polymers have many carbon-to-carbon bonds along their backbone. Having so many single carbon-carbon bonds in a row to spin around like this means the backbone can easily take on different shapes. Shown here is the characteristic random coil for a linear polymer. I'll explain why it's called that in just a bit, but I want you to see how thermal motion doesn't mean movement of the polymer location so much as it means movement of the individual mirrors. Thus, it looks as if it is wiggling. Note that this is the polymer conformation concept we discussed in the first lecture. Because the polymer's conformation, or shape, is constantly changing as it wiggles due to thermal motion, any useful description of its shape must be, again, some sort of average. Unlike the molecular weight averages, now the average is simply taken over time. In most cases, the average shape the polymer takes on is spherical. Obviously, there are exceptions to this, like DNA. Clearly, the conformation of DNA is not spherical. As in any case where the conformation of the polymer is not random, and therefore not spherical, the shape is maintained via specific stabilizing interactions of the mirrors. Thus, we have enzyme shapes and all sorts of non-spherical examples in the realm of natural polymers. To begin our conversation of how polymers behave in solution, let's start with how they behave in the bulk material. In the bulk, the molecules are entangled with each other. I often use a bowl of noodles to describe how long polymer molecules mix with each other in the bulk. Isolating just a single molecule, you can see how the shape of this polymer is roughly spherical. it is interacting with other MERS from other molecules and getting itself all wrapped around other molecules. But its shape is roughly spherical, and it has a specific size, or radius, to it. Taking the polymer out of the bulk and dissolving it in solution isolates the molecule. The only interactions the MERS have now are with the solvent molecules, not with other polymer molecules. The MERS may interact with other MERS from their own molecule, but that's it. Now, in what is referred to as a theta solvent, the MERS interact with the solvent molecules to the same degree as they interacted with other polymer MERS back in the bulk. Thus, the size of the random coil in the theta solvent is exactly the same size as the random coil back in the bulk. That is actually how a theta solvent is defined. From there, we have what are referred to as good solvents if the random coil gets larger in solution than it was in the bulk, and we have poor solvents if the random coil gets smaller in solution than it was in the bulk. In any of these cases, the shape the polymer molecule takes on is roughly spherical, and certainly spherical when considered over time, and is called the random coil. The term random coil being derived from the model used to describe the shape of a polymer is called the random flight model, or RFM for short. The model has many names. One of the more fun names is the drunkard's walk. We'll use the drunkard's walk description because it's the easiest to envision and clearly more fun. We start with a drunk propped up against a lamp post. I'll label the starting point here. This would be one end of a polymer molecule. The drunk takes steps in any random direction, but each step is always the same distance. This step represents the standard bond distance for our polymer. We will label the step length L. For a carbon-to-carbon bond, it is 1.54 angstroms. For the first step, the drunk can go in any direction, not because he intends to, but rather because he is drunk. Likewise, the carbon-to-carbon single bond can rotate, so each subsequent bond can go in any direction. Sort of. We'll get into the specifics later. Now we continue the process. The drunk, again, takes an uncoordinated step, which ends up being in any random direction. Similarly, the next carbon-to-carbon bond also rotates, and so we can progress along the backbone with each carbon atom being a junction where the remainder of the polymer backbone can lie in any direction. Eventually, the drunk passes out, or we reach the other end of the polymer chain. If the polymer has n number of carbon-to-carbon bonds along its backbone, we end on the nth and final step. Now, we have some definitions to clear up, the first of which is the contour length. This is essentially the distance that the drunk walked, along his path, mind you. It is calculated as the length of the steps times the number of steps taken. Note that because the drunk couldn't walk in a straight line, the distance he walked was much greater than the final distance he actually traveled. For all of his steps, he didn't get far from the light post. This is characteristic of a randomized flight path, hence the formal name for the model. We refer to the distance he ended up from the light post as r sub naught. It is the final distance as shown here between the two ends of the polymer chain. Hence, the r sub naught is called the end-to-end distance. The RMS, in parentheses, stands for root mean squared and is a technicality from how it is calculated. Clearly, as the polymer wiggles around, this end-to-end distance keeps changing. The root mean squared refers to how all of the possible steps and all of the possible conformations of a polymer can be averaged and a final r sub naught reported. Essentially, it requires the square of all the possible values, then being averaged and finally square rooted in order to yield a value with regular distance units again. The math is not extremely difficult, but the derivation is outside the scope of this course. Another, more commonly reported distance value for the random coil, described by the model, is the radius of gyration, given the variable designation r sub g. This requires finding the center of mass of the random coil and averaging the segment distance from this center of mass. If this looks familiar, that is because I mentioned it as one of the extra parameters the light scattering method can yield in addition to the weight average molecular weight. In this, the easiest version of the model, we have a relationship between r sub naught and r sub g, as shown here. These formulas have been derived in the reference texts, but are really standard for this model. Keep in mind that these formulas work only for this version of the model. It gets more complex from here. For right now, this version is referred to as the freely jointed version. And because even though the step lengths are kept constant, the direction of each step is kept as truly random, so the joints have no limitations. Because a polymer molecule is in three-dimensional space, and not confined to a two-dimensional plane like the drunk was, its full name would be the 3D freely jointed random flight model. Now, while the drunkard's walk was a fun game, and the freely jointed model is a legitimate mathematical model for steps in any direction, we need to make it a little more complicated if we want any hope in using it to accurately model a real polymer chain. Why? Because a polymer chain is much more restricted than a drunkard's walk. First off, a real polymer is composed of mers. Each mer has a specific number of carbon-to-carbon bonds that it contributes to the polymer's backbone. Knowing the chemical structure of the monomer residual, we can convert the degree of polymerization, small n, into the number of segments in the freely jointed chain, of which I purposefully represented as capital N. For ethylene polymers, acrylic polymers, vinyl polymers, and some others, there are 2 carbon atoms for each monomer residual. These are the joints in the model. Consequently, there are also 2 carbon-to-carbon bonds per monomer residual, so there are twice as many capital N steps for every small n degree of polymerization. The step length L is easily converted to the carbon-to-carbon bond distance of 1.54 angstroms unless another atom is thrown in the backbone, in which case an average must be taken. I'm going to assume you can figure that out at a later time. As a better approximation, we also have what is called the freely rotating version. This takes into consideration that the direction a real carbon-to-carbon bond will take is dependent on the previous bond direction. Namely, this is because the sp3 hybridized bond angle is about 109.5 degrees, which means the angle which any segment may take must be 70.5 degrees from the straight ahead direction. As represented here with the cone, this essentially allows the bond to rotate, but the angle must remain constant, hence the freely rotating portion of the name. There is still plenty of freedom for the steps to be in different directions. They just have to maintain a certain angle. Given the variable theta, and usually 70.5 degrees for carbon-carbon-carbon bonds, the formula used to calculate R sub naught, and or R sub g, takes on the same format as the freely jointed model above, but with a trigonometry term in parentheses before the NL squared portion. As you can imagine, the term in front ends up being larger than 1, and the freely rotating chain model predicts a larger size random coil for the same number of repeat units. With theta equal to 70.5 degrees, the trig term comes out to nearly exactly 2. An even more accurate size can be estimated if the energetic stability of the angles is considered. Here I have a portion of a polyethylene backbone with the hydrogens drawn explicitly. Remember that hashed wedges represent bonds going into the drawing plane, while the solid wedges represent bonds coming out of the drawing plane. Looking directly down one of the carbon-carbon bonds, we get what is referred to as the Newman projection of the bond angles. When the non-hydrogen groups, the R's here, are going out at 180 degrees from each other, this is the most energetically favorable position due to the lack of steric hindrance. This results in a trans anti-conformation. One of the least favorable positions would be the gauche conformation, where the large R groups are impeding on each other. Of course, the least energetically favorable position would be as the 2 large groups eclipse each other and are closest to each other. The angle at which the second R group makes from its position in the anti-conformation is defined as phi. Just like the last time, when we put constraints on the freely rotating chain, we end up increasing the estimated size of the random coil by adding another term in front of the NL squared equation. This term is a little more complex though, because one needs to average out the energies from the different conformations over all phi angles to calculate the second term in parentheses. This more complex version of the random flight model is referred to as the hindered rotation version, but it ends up being utilized in a more empirical form. Since most calculations for the hindered rotation chain equation would be tedious and probably still not large enough, the equation is simplified and semi-empiricalized. The two terms in parentheses are reduced to a single variable, shown here as C infinity. The single variable is called the characteristic ratio. It basically combines all of the different factors that contribute to the polymer chain not behaving as the simplest random flight model predicts. So it takes into account the bond angles and the restricted rotation due to steric hindrance, and essentially should yield the size of the random coil in a theta solvent. Actually, that's how it's defined. To determine the characteristic ratio for a particular polymer, one needs to use the random flight model to estimate the radius of gyration given the variable r sub g, r fm. Again, note the version used for this calculation is the original, simplest random flight model, the freely jointed chain version. All one needs to know is the bond distance L and the number of bonds along the backbone, capital N. So yes, the degree of polymerization for the sample will need to be known. Then, the actual radius of gyration of the polymer sample must be determined in a theta solvent. This is given the variable r sub g, theta, to distinguish it from the hypothetical r sub g we just estimated. Now, this radius of gyration has the characteristic ratio included in it. Thus, looking back at the highlighted portion of the equation, we simply take the ratio of the actual random coil, r sub g theta, and the hypothetical random coil, r sub g rfm, and square it to get our characteristic ratio. Now we can use this characteristic ratio for any molecular weight sample of this same polymer type. Most common polymers have their characteristic ratios documented somewhere. There is a table of some in the course material. Armed with the characteristic ratio and the molecular weight of a common polymer, you can now easily determine the random coil size in a theta solvent, or in the bulk for that matter, since they are equal. The question you're probably asking at this point is, what about in other solvents? Since most solvents for a particular polymer are not going to be theta solvents, we need a way to account for each polymer-solvent combination. The characteristic ratio is characteristic of the polymer type, hence its name. Now what we need is another parameter, shown as alpha here, to describe how the solvent interacts with the MERS of the polymer. This parameter is referred to as the coil expansion factor. It takes into account many things related to the solvent, like the exclusion volume and its interaction with the repeat units of the polymer. Obviously, this expansion factor, alpha, will be different for every solvent. Actually, it will change for each polymer-solvent pair. It is defined and determined in much the same way as the characteristic ratio was. Here, though, the r sub g ratio of the solvent to theta solvent is used instead. To determine the expansion factor, we simply start with the same r sub g theta we measured from the last slide for our denominator. This time, however, we have the radius of gyration as measured in the particular solvent of interest. As you can see, we're using r sub g solvent to distinguish this value from any of the other r sub g values we've discussed so far. This ratio is squared to yield alpha, our expansion factor. Note that ratios of either r sub g or r sub naught values can be used to determine alpha. Now, if you remember how we defined good, theta, and poor solvents, it's easy to see that this expansion factor is all that is needed to distinguish between them. By definition, a theta solvent's expansion factor is 1. Since a good solvent is one that interacts with the MERS to a greater extent than the MERS do to each other, the polymer coil swells up beyond the size it has in the bulk, and we see that alpha is greater than 1 in this case. The reverse is true for a poor solvent. The interaction between the MERS and the solvent is so poor that the MERS prefer to interact with each other than the solvent. Thus the coil condenses and the expansion factor for a poor solvent is less than 1. Expansion factors for various common polymer-solvent pairs are tabulated similar to the characteristic ratios. Let's go over a very common polymer as an example of how these calculations work. For a 1 million grams per mole polystyrene sample, what's the end-to-end distance and radius of gyration in the bulk? Starting with the equation for the simplest random flight model, the freely jointed chain version, we see that all we need is capital N and L. I always start with calculating the end-to-end distance, even if the question doesn't explicitly ask for it. It's always a stepping stone to R sub G anyway. We recognize that all of the bonds in the backbone are carbon-carbon bonds, and that they'll have a bond distance of 1.54 angstroms. Okay, now I need capital N, the number of steps we take along the backbone. A quick look at the chemical structure of the polystyrene repeat unit, and we see that there are 2 bonds per mer. Great. Capital N is equal to twice the number of mers in the polymer. Oh, that means we need the degree of polymerization. Not a big deal. We know how to get that value too. We just divide the mass of the molecule by the mass of the mer. Since we have them in units of grams per mole, we'll just keep them there. 1,000,000 grams per mole for the polymer molecule, and 104 grams per mole for the repeat unit, and we see that there are 9,615 repeat units per molecule. Alright, now we're getting close. Capital N is twice the degree of polymerization, and that gives us over 19,000. Now, solving the freely jointed chain equation for just the end-to-end distance, we can plug in our values and end up with 214 angstroms for R sub naught, and 87.4 angstroms for R sub G. Now let's take a moment to realize what these values mean. If we take the contour length of the polymer, the length of the polymer if it was completely stretched out, it's capital N L, which is 19,230 times 1.54 angstroms. This is a pretty large number, almost 30,000 angstroms to be exact. Converting the units, this is 3 micrometers. That means that this polymer molecule is longer than a bacteria cell. However, because it coils up to a certain extent, we estimate the radius of gyration is just 87.4 angstroms. That's the size range we're talking about. The polymer is constantly in motion and averages around this R sub G value, but that's only an average. It can get much larger if chance allows or specific interaction dictate it, but we'll get into that later. This is still only an estimate. For a more realistic size, we can utilize the hindered rotation version, and all we need is the characteristic ratio for polystyrene. Oh, it's 10? Great. Now we just put the number into the equation, and we get an R sub G theta of 276 angstroms. This is still pretty small compared to the contour length of 3 micrometers, but it is larger than the estimated R sub G value above. In this course, the predominant solvent we'll be interested in is water, and the polymers are water soluble. We can use the corrected random flight model, which uses both the characteristic ratio, C infinity, and the expansion factor, alpha, to estimate the size of the polymer in solution. Now, if the polymer is a polyelectrolyte, the situation gets more complex. As the extent of ionization increases, the polymer swells. This happens as the pH is increased for polyacids, and as the pH is decreased for weak polycations. The polyacid is shown here. The negative charges along the polymer repulse each other due to Coulombic forces, and the chain tries to separate the mers as far apart as possible. This extends out the polymer. As you would imagine, the higher the extent of ionization, the more extended the polymer chain gets. Because of this swelling, the radius of gyration becomes much larger than the corrected random flight model estimated for the neutral polymer. Now, no matter what the extent of ionization is, even if it's a quaternary amine in the mer, adding salt decreases the size of the coil. Why? Because the extra ions in solution now begin to screen the repulsive Coulombic interactions between the charged mers. Note that it is still swollen, however, in comparison to the original estimated size according to the corrected random flight model. Eventually, as more and more ions are added to the solution, the polyelectrolyte's random coil size reduces to its estimated size as the Coulombic interactions between its mers are all but completely screened out. Keep in mind that the R sub G here is changing, while the molecular weight of the polymer is not. The contour length stays the same, but the average distance from the center of mass, the R sub G, is all that changes. That's why I was so careful to say the size of the coil, and not the size of the polymer is what's changing.